got the idea for this video from a couple comments on another one of my videos. You guys were debating which filament was best for what I 3D print. So today, we're going to test 3 popular filaments and see which one is the best for model rocketry. We'll print identical parts from each filament, test them, and then compare them to each other. The special thing about 3D printing is that it can give you parts like fin alignment jigs like what Joe Barnard uses, or nose cones, couplers, motor mounts, and sometimes even an entire rocket's body. So today, we're going to be focusing on FDM printers. FDM printers are basically what you think about when you think about 3D printing. FDM printers print layer by layer with melted filament, and that is what gives it its strength. The printer I'm using in this video is my Bambu Lab A1 Mini, and I absolutely love this thing. It's incredibly easy to use and gives you extremely precise parts. This isn't a sponsor, but if anyone from Bambu Labs is watching, give me a call. The only issues that you can run into with this thing is its build space and the fact that it can't print higher end filaments. Things like carbon fiber or anything with glass inside of them. So to start the design process for these tests, first I grabbed a nose cone off of Make a World from a creator. That nose cone is going to be used for our heat testing, and then I'm going to design a couple of extra parts like bars, spheres, and cubes. The goal for this first test is to identify which nose cone softens or warps fastest under heat, and to check for any deformation that could happen during flight. All of the settings we're going to be using for each individual filament comes straight from the manufacturers, and that is to keep everything as fair and consistent as possible. For our PLA prints, these are the settings we're going to be using. Okay, the next is on to PETG. For our PETG settings, we're using the manufacturer's recommended values again, just to keep everything consistent. But for PETG, you'll notice that the print speed is actually much slower than it was for PLA. And that is because PETG tends to be stickier and more temperature sensitive than PLA is. Which means if you print too fast, the layers don't have enough time to harden and bond properly, which if that happens, can lead to stringing, blobs, or poor layer adhesion. And with printing with PETG the first time, I had a couple problems. It is 3:37 in the morning, and this printer is still messing up on this PETG. Here, look, take a look. But once we had sorted those problems out, we were ready to move on to Nylon. For Nylon, you'll notice that you actually have to print it much slower and much hotter than PETG or PLA. And that is because Nylon is a very temperature sensitive material and it needs more time to bond properly. Printing slower helps prevent warping and ensures stronger, more consistent layer adhesion. When printing with Nylon, you need a couple of different things that you wouldn't need with something like PLA. First off, you need a filament dryer. A filament dryer is exactly what it sounds like. It's made to dry your filament. You might think to yourself, what do you mean dry my filament? And you'd be right to think that. But filaments like nylon are what we call hygroscopic.
Hygroscopic,
which basically means they pull in water from the air. So if you're on the coast or in a very humid area, if you're using nylon filament, it could get completely soaked all the way through the entire roll in just a day. The way you can tell your filament isn't dried is if you start printing and you hear a little popping sound like this one here. That means that the water inside of your filament is boiling when it goes into the nozzle. So if you're using something like nylon or another extremely hygroscopic filament, you need to dry out your filament, whether that be a filament dryer like this or just by throwing it in your oven for a few hours on low temperature. Now that we've got all of that covered and the nose cones printed, we can begin the heat resistance test. Now you might think, shouldn't the bottom of the rocket be tested for heat? And yeah, you would be right, but when a rocket flies, the friction of the air on the nose cone can generate an extreme amount of heat, which means if the tip of your rocket is 3D printed, It can soften, warp, or bend, and that could throw off your entire flight. For this test, I'm going to be using a heat gun that can reach up to 250 degrees Celsius. Each nose cone will be mounted at the same distance away from the heat gun, and we will continue the tests until they are completely unflyable. Then, we'll check for any softening, warping, or the deformation that happened during the test. After the test, the results were pretty clear. The PLA and PETG handled the heat the worst. As a matter of fact, the PLA and PETG started deforming within just 15 to 30 seconds of being in the test. But the nylon stayed strong. So strong, in fact, that it actually wouldn't budge. I originally let it go for about 5 minutes at 2 inches apart. I ended up having to actually move the heat gun even closer and blast it for another 10 minutes. And still, nothing happened. Just to be safe, we also tested the nose cone standing up and the heat gun in the same position. And just like before, the PLA and PETG nose cones both started deforming at, again, just the 15 or 30 second mark. But for the nylon, I actually had to move the heat gun even closer to the point to where it was almost touching it. And even after all of that, all it did was melt a little bit. So the winner for test 1 is obviously the nylon. But that doesn't come without some costs. The goal for test 2 is to measure bulk strength and interlayer adhesion. Whenever you 3D print something, it's not one solid chunk of material. It's built up layer by layer, and because of that, 3D printed parts are what's called an isotropic, which basically means the strength changes depending on the direction of the layers, which is exactly where the print has to rely on the adhesion rather than continuous material. We'll print one test bar per filament. Each filament will follow a standard bar shape. Originally, we had done it at about 120 millimeters long by 15 by 15 millimeters. But we actually had to change it to 175 millimeters long so that I could actually break it. We'll label each one clearly and test each sample in the same manner as the one before, just so we can compare each filament's performance. For this print setup, we're using all of the same settings as before. Originally, I made the infill at something like 50%, but whenever those printed off, I realized that they were way too strong and there was no way I'd be able to break them. I originally printed them way denser, like 50% infill. Those are very, very thick, and there's no way I'm gonna be able to break them. We're gonna be testing that with this thing. This is a luggage weigher. It's made to go up to 110 pounds, so I don't know if they're gonna break. Probably not, but we're gonna find out. During the process of the PLA brake test, I realized once I'd actually broken it, that I wasn't actually even looking at the weight that it pulled. I was just trying to break the bar. So I printed it again and redid the test. This time, I actually looked at the weight. And for the PLA bar, it broke between 30 and 40 kilograms. Not too bad for just PLA. But now, it's onto the PETG bar. Wow. So once we had finished the PETG test, we looked at both of them. So the PLA broke just between 30 and 40 kilograms. The PETG broke at just over 45. And the nylon, well, it didn't break. Ooh, that one didn't break. And the reason it didn't break is actually pretty interesting. The reason it didn't break is because I pulled it on the wrong side. I was pulling it the opposite way of which it was printed. That being said, I reprinted it using the same filament and the same settings. This time, it got to 47 kilograms before it even broke. And it didn't even fully break in half. It broke just like the previous one, but it didn't actually fully come apart. Alright, for test number 3, we're testing impact toughness. This is where we find out how well the filaments handle real-world abuse. Things like hard landings or dropping it accidentally. For this test, we printed 2 different objects for all 3 filaments. A 50mm sphere and a 40 by 40 square cube. And again, we're using the exact same settings as we've previously used on every test in this video. For the first test, we're going to be throwing each one of these samples at a concrete wall with the same amount of force. This is going to show how brittle or flexible each material is when they impact the wall.
crack right there.
For the next test, we're going to be doing a cinder block drop. Each sample is going to sit on one cinder block while another cinder block is going to be dropped on top of it. This simulates a hard landing or something else falling on top of your rocket before you even make it out to the pad. After each impact and test, we can see that the PLA actually held up the best out of all three of them. That's not because PLA is just a better filament, it's just because I accidentally put the infill way higher than the other two. So this one was way more dense, which means it was able to take a much harder hit and get back up. Taking a look at the other two, we can see that the PETG completely broke. And since we have to void the PLA because I accidentally put the density too high, that means that the nylon is the winner yet again. Alright, next we can talk cost. PLA is pretty cheap. I got this roll off of Amazon for about $13, and $13 for a kilogram of filament isn't too bad. Same thing goes for this PETG. I bought this PETG for also just a little more than $13. But the nylon, on the other hand, the nylon was more than double the amount of either of these filaments. 1 kilogram nylon roll is more than $33 on Amazon, so that's more than both of these filaments combined. But now that we've talked about the cost, we can talk about how well they actually printed. For PLA, it was obviously the easiest. All you really needed to do was put it onto the printer and let the printer do its thing. PETG, on the other hand, that was just a little bit more difficult because PETG required slightly higher temperatures and slower printing. But once we got the hang of it, it was pretty much as easy as PLA was. But nylon was a different story. It needed to be completely dried for several hours before printing, and it needed to be printed slower, so it took much longer. I also needed to put some glue onto the bed every time I needed to print something so the first layer would stick correctly. But once we got all that dialed in too, it was also not too bad to print with, and it printed out some pretty good parts with just a little bit of tweaking. So in the end, I think the best type of approach to this kind of question is that it's going to be a mix, maybe even all three types. Because for prototyping, you can easily, affordably, and reliably use PLA or PETG. But for the actual part you're going to use, you could use nylon. But also, taking into account for these tests, they obviously aren't the most accurate. Some of these filaments are just much better at different things, so you really have to test every single one of them. So anyway, out of all three of these filaments, if you need something that's going to be strong and durable, go with the PETG. The PLA, on the other hand, is good if you need something super rigid. And the nylon is great if you don't really care about being rigid, but you need something that can really handle the heat. So for the purpose of this video, I'm going to say it's a tie for all three. And the reason that it's a tie is because you can't really compare two things that were made for separate purposes. So anyways, that's it for this video, guys. Thank you for watching, and remember to stay curious and aim for orbit.